So ultimately, where we're going in this chapter is towards this general overall thermodynamics equation, which is delta G, which is what we call the Gibbs function. And the Gibbs function is often referred to as the free energy of a reaction, which is the amount of energy that's available to do useful work, and that's measured in kilojoules per mole. And the Gibbs function is equal to the change in enthalpy, delta H. And just to remind you, the delta H, the enthalpy, that's just the thermal energy at a constant pressure, that we could also write as Q of the reaction at a constant pressure. That's also measured in kilojoules per mole. And then we're going to introduce a new concept also in this chapter, that of entropy and also temperature, but temperature is not a new concept to you. So we're going to have another term here, minus T delta S, where T is the temperature, that's on the absolute temperature, so using the Kelvin scale. And then delta S, which is the entropy of the system. Entropy, as we'll be discussing, that's basically the energy dispersal or randomness of the system. And that's measured in joules per Kelvin, not kilojoules. Where delta G, the Gibbs function, is the amount of energy available to do useful work, we can also think of the entropy as the energy of the system that's not available to do useful work. So it just dissipates into the overall universe. So that's where we're going in this chapter, and we're going to be addressing each of these new thermodynamic functions separately. We'll start with entropy, and then the second half of this unit, we'll be talking about the Gibbs function, the free energy of the system. So spontaneity, this is a term that we use simply to describe whether or not a reaction, as written, let's say A going to B, whether that reaction will actually occur on its own without any outside intervention. We might need to give it a little kick to begin with, and we'll talk about that later. But once it's going, it doesn't require any other outside intervention for that reaction to keep going. That's what we call a spontaneous process. Now, a non-spontaneous process can still proceed in the direction that it's written, but it would require some kind of outside energy being continually added to the system to keep the process going. Now, don't confuse the word spontaneous with it happening instantly. Some spontaneous reactions are fast, some are incredibly slow. Now, a simple way to think about this, a spontaneous process, if we have an incline and I have a ball at the top of the incline, without any outside intervention, that ball will spontaneously roll down the incline. Whereas if we have the same incline, here I'll flip it just because we're keeping the convention going from left to right for the progression of our reaction. All right, if this is the reaction arrow, that bottom process here won't occur on its own. It requires some kind of energy input in order for that reaction to proceed. Now, there are many types of reactions that occur all around us every day that we just take for granted are going to happen spontaneously. For example, if you put some material that has a red dye in it and you drop it in a glass of water, fairly quickly that red dye is going to dissipate throughout the whole solution, and it will go from this picture to being thoroughly red. That would be a spontaneous process. We don't need to do anything else to this overall system to get that dye to disperse completely, so it looks completely homogeneous. Here's a balloon, and I think we all have a pretty good idea of what happens if we throw a dart at this balloon. What's going to happen? All right, it's going to puncture the balloon, and whoosh, all of a sudden the air escapes from it. If you get injured doing your favorite sports event and you want to put a cold pack on your muscles to make them feel better, okay? Well, cold packs, you start shaking it up, and there's a reaction that happens, and it's a spontaneous reaction, and it gets colder. Hopefully, none of you have had this experience in your car of having to use the airbag that's deployed when you're in an accident. But when that happens, there's a reaction that takes place that causes that airbag to expand very, very fast. That's a very fast reaction. These are all spontaneous. Some of them are slow. Maybe the dye dispersing into the liquid is rather slow. But the airbag, boy, you hope that's going to be fast if you're in an accident. That's not just compressed air being opened up. That's an actual chemical reaction where you have some sodium azide here, NaN3 in solid form, is very, very quickly decomposing in here. We have 2 molecules of sodium azide will decompose into 2 sodium atoms and 3 molecules of nitrogen gas. Here's something else that you're all probably familiar with: ice melting into water, or water freezing into ice. We studied what happens with this conversion, right? There's an equilibrium here when we're at the melting point or freezing point of H2O, which is 0 degrees Celsius under normal pressure, okay? We have this equilibrium that's established. But what if we're not at 0 degrees Celsius? What's going to happen at 25 degrees? If we're at 25 degrees Celsius, I think we all have a pretty good idea that this reaction going from left to right, going from the ice to the water, at 25 degrees, this is a spontaneous reaction. We don't need to do anything else to the system to get that H2O in the solid phase to change into H2O in the liquid phase. Now, the same is true if we're at a lower temperature. Let's say we have the system at negative 10 degrees Celsius. We're below the melting point. Well, that process going from liquid to solid is also going to be spontaneous. Now, that also means that if a reaction as written from left to right is spontaneous, that means the reverse reaction is non-spontaneous. Those will go hand in hand. So for example, at 25 degrees, ice melting into water is spontaneous. That means that the reverse reaction is non-spontaneous. That also could be said in reverse. Ice going into water is non-spontaneous at negative 10 degrees Celsius. And the reverse reaction, well, that's non-spontaneous if we're at 25 degrees Celsius. Here are some more examples. Here's some glucose. Solid glucose combining with molecular oxygen gas will give us carbon dioxide gas and H2O. You may recognize this as a combustion reaction. And for you biologists out there, you'll also recognize that this is what's happening in our cells to create energy. This is what we call cellular respiration. This has an enthalpy value associated with it of negative 2,801 kilojoules per mole. So we would refer to this as an exothermic reaction. Remembering that the term exothermic means that the system is losing thermal energy to the surroundings. And that's why we apply a negative sign to this number, because it is the energy leaving the system into the surroundings. So it's what's happening to the flow of thermal energy with respect to the system. Anyone who lights a match to something that's combustible will realize that this is a spontaneous process. Although you do have to ignite it, and we'll be talking about that little bit of activation energy that we need to add to a reaction to get it to go. But once this reaction starts, it keeps on going without having to give any more energy into the system. So this is a spontaneous process. The reverse of that process is non-spontaneous. Well, here's the reverse of that process. Carbon dioxide mixing with H2O to give us glucose and molecular oxygen. Although once again, you biologists out there will recognize that this is photosynthesis. It's the same reaction run in reverse. Photosynthesis is an endothermic reaction, meaning that we need the same amount of thermal energy, but now it's going into the system for this reaction to run. So once again, this reverse reaction here is non-spontaneous, meaning that it requires input of energy to proceed as written. And indeed, this reaction will not occur unless you have the energy provided that comes from the sunlight. Now, as I mentioned already, spontaneous does not necessarily mean that it's going to be fast. It just means that the reaction is going to proceed as written without any extra input of energy. Here's another reaction that you're very familiar with. This is iron rusting. The iron is being oxidized. We have solid iron is mixing with molecular oxygen to form iron 3 oxide, otherwise known as rust. This is still a spontaneous reaction. Anyone who leaves their metal things outside for a long period of time will realize that over time it will rust. But it doesn't happen instantly, but it's still a spontaneous reaction. Here's the change in enthalpy for that reaction. This is also an exothermic reaction. And just to drive the point home, there are other things like the decay of carbon-14 into stable products. In the case of carbon-14 and carbon dating, it's very, very, very slow. This reaction does occur spontaneously. The half-life for this reaction, the time it takes for half of the radioactive material to decay into something stable for carbon-14 is on the order of 5,700 years. It's a very, very slow process, but it's still spontaneous. Now, you may have noticed that a lot of these spontaneous reactions that I've been describing also happen to be exothermic. And for a long time, scientists thought that there was a direct relationship between a process being exothermic and it being spontaneous. But there is something else going on here. It's not just the enthalpy that's driving spontaneity, as we'll see. And that also means that there are some endothermic reactions that are still spontaneous. For example, that cold pack, right? That's an endothermic process, but it's still spontaneous. Here are a few more things to think about. So when we talk about heat transfer, it's always going to be from a hotter substance into a colder substance. And if you put them in contact with each other, then we can have a heat exchange or an exchange of thermal energy. When you mix something that's hot and something that's cold, the heat transfer goes in this way until there's an equilibrium between the two. We've reached a state of thermal equilibrium. There's that word again, equilibrium. We have a whole chapter coming up just on equilibrium, but you're seeing it a lot already. So in this case, we're getting equilibrium just due to the heat transfer. But what happens when you have gases? Let's say we start with this contraption on the right where we have a partition here in the middle, okay? And we have ideal gas A on the left, and I don't know why the book says A prime. Let's go ideal gas B. And we're going to keep everything the same, all right? We have the same temperature, so there's no changes here. The same number of moles of A, the same number of moles of B, and we'll start them at the same pressures. There's no pressure volume work at play here. So there's no PV work, which means that there's no internal energy. Internal energy, just the energy of the system. But I think we all know what's going to happen if we remove that partition. The gas A molecules are not going to just stay on the left, and the gas B particles are not going to just stay on the right. They're going to mix completely. So here, let's do B as in red here, and let's put A in blue. If we start with that on each side, we're going to end up with both gases being equally dispersed on both sides. But there's no internal energy to force that. So something else must be driving what seems to be a random dispersal of the molecules. So what's driving that? Well, it's called entropy. So now we have two thermodynamic factors that we need to consider when deciding whether something's going to be spontaneous. We have the change in enthalpy of a system, and we have the change in entropy, which is something that we'll be describing more in the first couple of lectures for this unit. Here's just a few more examples to drive the message home. In this process of the ice melting into the water, energy is going into, here let's change this from what the textbook says. The energy is going into the system, and then in doing so, that's going to cause the solid to go into the liquid phase. And this is going to be spontaneous above 0 degrees Celsius. But this is energy in. Energy into the system, that means it's endothermic. Yet this reaction of it melting is spontaneous, but only when we're above 0 degrees Celsius, just like I mentioned in the previous slide. And if we look at the reverse reaction, the liquid going into the solid form, that's going to be energy is coming out of the system. So that's going to be exothermic. And as we discussed, that's still going to be spontaneous, but only when we're below 0 degrees Celsius. Now, you may think, wait, how can that be exothermic? We're making ice cubes. That's giving off heat, but we're making ice. So how can that be? Well, if you've ever gone to the back of your freezer when that's happening, you'll know that the freezer coils in the back are very, very hot. Here's another example of a spontaneous reaction. This is where you take some baking soda, which is sodium bicarbonate, and you mix that with vinegar. And if you remember, vinegar is a 5% solution of acetic acid, CH3COOH, and you get sodium ions in solution and acetate ions in solution, and you make some liquid water, liquid H2O, and you make some CO2 gas. The delta H for this reaction is a positive 48.5 kilojoules per mole. It's endothermic, and as was shown here, energy is going into the system. That may seem confusing to you because it says energy in, and we say energy is going in and it's endothermic. But what's really happening here is that this reaction is spontaneous, not because it's exothermic. It's not, it's endothermic. So it's spontaneous for other reasons, but when this reaction occurs spontaneously, it is taking energy from the surroundings into the system. So the surroundings get colder. That's why if you put your hand on this reaction vessel, it's cold. It's an endothermic reaction. But something else is going on that makes this reaction spontaneous. It's not just whether it's endothermic or exothermic. Right? Thermal energy alone does not dictate spontaneity. The other thing to consider is entropy, and that's what we're going to be talking about in class. Now let me just give you a brief introduction to entropy here, and it has to do with the second law of thermodynamics, and this comes from Rudolf Clausius back in 1865. And entropy is simply a measure of how the energy is dispersed in a thermodynamic system. You may have heard of entropy as simply adding to the disorder of a system. That's another way to just think of spontaneity as depending on how dispersed things are in a system or during a process. That's the same idea as if they're more dispersed, that means there's more disorder. The second law of thermodynamics is that the total entropy of the universe, not just the system, but the entropy of the universe will increase in any spontaneous process. So now that you understand what a spontaneous process is, you do have something that's happening spontaneously in the system that does have an effect on the surroundings. But the delta S, or the change in entropy of the universe, that's the one thing that is going to increase in a spontaneous process. That means this has to be greater than zero, right? The system is typically your reaction that you're studying, and the surroundings is everything else. If you have an increase in randomness, your delta S is going to be a positive value, greater than zero. A decrease in the randomness, then delta S is going to be negative. So this is positive, this is negative. Something that has high entropy means that you have a lot of disorder. Something that has low entropy just means that it is more ordered. There's more organization. There's less randomness in the system. Now, I'll also remind you that delta S, just like delta H and a lot of the other things that we've been studying, these are all state functions. But unlike what we were able to do with enthalpy, we cannot measure entropy directly. For enthalpy, we were able to get that from the temperature change in calorimetry experiments, but we can't do that directly for entropy. But what we can do is use this mathematical description of entropy provided to us from Rudolf Clausius, which is that the change in entropy of a system is going to be equal to the thermal energy of the system, Q, divided by the temperature of the system. So Q, this is something that we can measure using, for example, calorimetry. Enthalpy itself is simply Q that we would measure at a constant pressure. The reversible part, it's a special case of when things are what we consider to be a reversible process. We're not going to focus that much on that part of the definition, but you should be aware that this really is under an ideal circumstance where we have what's considered to be a reversible process, which is one that happens so slowly and at such an incrementally small change that you can run the reaction forward or reverse just by doing some other tiny little change to the overall system. But for our purposes, we're going to consider that the enthalpy at constant pressure here, so the Q, divided by the temperature of that system, we can use that to calculate what delta S is. And we'll be using that for some examples. Of course, we also have something that Clausius didn't have at the time, and that is we have all of these values listed for us in Appendix 4. Not delta S specifically, but the standard molar entropies, which are derived from the third law of thermodynamics that we'll cover in lecture, as well as how to calculate delta S from these values listed in Appendix 4. So I will remind you that Appendix 4 in the back of your textbook is rich of lots of information and other thermodynamic properties of many different types of compounds. So you will be using Appendix 4 a lot to get this information. So ultimately that will get us back to this grand equation that we started this little chat with, where the delta G, the Gibbs function, is equal to delta H minus T delta S. It's the delta G, that's what's ultimately going to tell us whether a reaction is spontaneous or not, and that will be due to the interplay between the enthalpy and the entropy of the reaction that we're looking at. And again, in lecture, we're going to pick this up, continuing along with entropy, and then we'll get back to the Gibbs function later on in the chapter. All right, so the overall theme here is spontaneity, spontaneous. What does spontaneous mean to you? What does that word conjure up in your mind?
Randomly.
Randomly.
Intentional.
Unintentional. Spontaneous. Unintentional, random. What else? Happens all of a sudden. Out of nowhere. All of a sudden. So I'm getting the feel of like unanticipated, unexpected, but when it happens quickly. Is that what I'm getting from you guys? All right, that's good. Now, from a thermodynamic sense, all right, this is spontaneous means something a little different, right? It kind of means all of those, but it kind of doesn't, all right? Spontaneity, spontaneous, if I have a reaction that's written like this, A going to B, if it's spontaneous, it doesn't necessarily happen unexpectedly, and it doesn't necessarily happen like that, okay? Fast, that's pretty good. Fast and unexpected. No, all spontaneous means, anyone do you know? The actual thermodynamic definition? Once it starts, it doesn't need an input of energy for it to keep going. It will happen on its own. Now, as we'll learn later on, sometimes you need to give it a little kick, okay? But once it's going, it keeps on going, right, to completion in this case. This arrow, this solid arrow going from left to right, meaning that A will completely turn into B. And it's spontaneous, but it's completely independent of how fast. All right, and in the video I gave you a couple of examples of that, like rust. Right, you leave something metallic outside, and eventually it will rust, but it takes a long time. Rusting is not instantaneous. For all you carbon daters out there, right? If you want to know how old something is, you take carbon-14, which is radioactive, and you wait for it to decay into something stable. And you can measure how much carbon-14 there is versus carbon-12, and you can figure out how old something is based on the ratio of radioactive carbon-14 to non-radioactive carbon-12. This is a spontaneous reaction, but it takes a really long time. So the time it takes for half of the material to decay is on the order of 57,000 years. But it is spontaneous. Okay? And the ultimate point of this chapter is to be able to look at a number of things going on in a reaction and be able to decide if the reaction is spontaneous or not. This really is the master equation. So we're going to focus on delta G is equal to delta H minus T delta S. Now we're going to do a little worksheet here in a moment. I'm skipping all the stuff that you should have watched and taken notes on already. We're going to do this worksheet today, but as we're doing this, I want you to stay focused on the second law of thermodynamics, which states that delta S of the universe is equal to the change in entropy of the system plus the change of entropy of the surroundings. And the second law of thermodynamics tells us that for a spontaneous reaction, delta S of the universe is always increasing. It's always greater than zero. The problem with this is we're used to working in the system, measuring what's happening in the system. That's our little reaction beaker. Or when we do coffee cup calorimetry, it's what's in the coffee cup. The problem with this is we need to know what the entropy of the universe is, okay? And I don't know, the last time I checked, but the universe is really, really big. Who am I? Who am I?
Carl Sagan.
Carl Sagan. All right. You guys have no idea who Carl Sagan is. All right. And it's really, really difficult to measure what the effect of an experiment is on the universe. Okay, but ultimately, this is what the second law is telling us. But this really is the same equation as the delta S of the universe equation. It's just rewritten in a way that we can measure everything that's happening in the system. So let me emphasize, this is all of the system, okay, independent of the surroundings. And when we get there, I'll derive it for you so you'll see that delta G actually has delta S of the universe in this term. Okay? So we're going to practice with this idea. Now, enthalpy, let me go over a couple of other terms that you should know, right? Enthalpy, that's thermal energy, right? So if thermal energy is going into the system, what do we call that? Endothermic. And what sign, plus or minus, do we put on that energy? It's a plus, okay? This is our convention, okay? If it's exothermic, that means the energy is going out of the system, and we put a negative sign on that, okay? It's not negative energy. It's energy. It's the flow of energy. The negative and the positive sign is just our convention to show us which direction that energy is flowing, either into the system or out of the system. So the first example here, if we're burning wood, we're going to describe what's happening to the enthalpy change and the entropy. So the first example here, if we're burning wood, we're going to describe what's happening to the enthalpy change and the entropy change. So you're burning wood, you're having a little campfire, and assuming you get it started, which isn't a given, no matches, okay, maybe you have your little striker, you get it lit. Now, is burning wood, is that going to be an endothermic or an exothermic reaction? You know that the energy, the thermal energy is coming out of the system because you can feel it. You're sitting there, you're getting warm, okay? So this is an exothermic reaction. So what is the sign, positive or negative, on delta H if we're burning wood? It's negative, right? It's a negative because the energy is coming out. It's exothermic. Now, what about the entropy? Now, you have to watch the video to understand what entropy means. Right? People commonly refer to it as disorder, but it's really just the dispersal of energy. The dispersal of energy. All right, so when you're burning fire, or when you're burning wood, sorry, what do you think is happening to the entropy of the system? Is it increasing or decreasing? Increasing, okay, 50-50 chance, but why?
It's radiating heat.
So it's radiating heat, okay. It's easy to imagine that if something is exothermic, it's giving off energy, it's easy to think that that's going to be spontaneous. But remember what spontaneous means. It will happen on its own without any more input of energy to keep it going. And in the video, there were several examples of reactions that give off thermal energy, but they're not necessarily going to be spontaneous. And the reverse is true too. Not everything, like you can get a sports injury and you break open a cold pack, right? That's a spontaneous reaction, but it's getting colder. The surroundings is getting colder because the chemical reaction is absorbing thermal energy. But that's also spontaneous. So you can't assume that just because it's giving off energy that the entropy is necessarily increasing. Okay? We got to be looking at something else, right? Let me rephrase what I just said. You can't assume that if it's exothermic, it's going to be spontaneous. That's the same as giving off thermal energy. Let me write the reaction. Here, let's burn some wood. Wood is mostly cellulose. Anyone know what the chemical formula for cellulose is? That's right, C6H12O6. That's right, it's the same as glucose. The difference is how they're linked together. But if you want to know more about that, you have to take my biochemistry class. But let's take some cellulose, all right? Mix that with some oxygen. This is a combustion reaction. What are the common products of a combustion reaction?
Carbon dioxide.
And water. CO2 plus H2O. Let's put some coefficients in here to balance it. And let me put the states of matter. All right, this is a solid, this is a gas, this is a gas, and this is a gas. This is something that we're going to be focusing on a little bit, all right, later on. Let's start now. Take a look at this reaction. The reactant side, we have 1 mole of something that's solid and 6 moles of a gas. And look at the products. 12 moles of gas in the products. Okay? And if you think about entropy as the dispersal of energy, or the randomness of a system, if you go from solid to liquid, that's getting more dispersed. And when you go from liquid to gas, that's really getting dispersed. So you can actually predict a lot about the entropy increase just by looking at the states of matter and how many moles there are, especially when it comes to gases. All right? So make a little asterisk in your notes about that. If you have moles of gas that are increasing in the products, that's a sure sign that the entropy is increasing in the reaction. So looking at it this way, we can say that the change in entropy, delta S, is that a positive or a negative? It's a positive, right? We're increasing entropy. Now we've got a good idea. If it's spontaneous, it's not only giving off thermal energy, right? So delta H is negative, right? But delta S, the entropy is increasing of the system, all right? And if we put these both in the context of our grand equation here, delta G is equal to delta H minus T delta S. Let's take a close look at this. In this case, delta H is a negative value, and delta S is a positive value. All right? Everyone see what I'm doing here? So what must the sign of delta G be? Positive or negative? Take a look at this. We've got delta H is always negative, and delta S is always positive. All right, look at this equation. What's the sign on delta G? It's always negative. Okay? Now I told you earlier that this equation, delta G equals delta H minus T delta S, is the same as our second law of thermodynamics. If it's a spontaneous reaction, right, delta S of the universe always increases. And when you rearrange that, okay, into this equation, it will always be spontaneous if delta G is negative. But you have to come back to a later lecture to have that connection made for you. Right now, I'm just telling it to you as a rule. And I guess I should have started by asking, when you burn a fire, I said it again, when you burn wood, inherently, is that a spontaneous reaction? If you light it and it's going to keep on going without you adding any more energy. You might say, oh, but the fire dies and you have to turn it around and whatnot. What's dying is it's starving for oxygen. You just need to, get more oxygen in there. Well, that's one of the reactants. But if it has plenty of cellulose and it has plenty of oxygen, it's going to keep on going. This is a spontaneous reaction, okay? And as we've just intuited, delta H is always negative, the delta S is always positive, so you can see here that delta G, for a reaction that we inherently know is spontaneous, we know that delta G is going to be negative. Okay? Now, do you guys want to work in groups on the rest of this and I'll float around, or should we just kind of work through it? Why don't you guys give this one a try? You're in your groups, okay? Just do this next one. let's bring it in, all right? And in the process of going through this, we'll reinforce some definitions, okay? Remember that in this form, and this is the master equation that we're really focused on throughout the whole chapter, right? This is all in terms of the system, whereas the second law of thermodynamics, it's universe equals system plus surroundings, and the surroundings, that's what's hard to measure, okay? Because the surroundings is everything else. So we're just focused on the system here, okay? And entropy, all right, more dispersion, more disorder, all right, dispersion of energy, really. But people like to think of it as just chaos and, randomness. That's fine. That works, okay? So water evaporating from a wet sidewalk. So let's just think about, with respect to the enthalpy, the heat, okay? When water evaporates from a sidewalk, is that endothermic or exothermic? And why? Endothermic. Are we all agreed that it's endothermic? And why is it endothermic?
It's taking in energy.
Right. You're going from the liquid phase to the gas phase, right? So it takes energy, just like we talked about in the last chapter. It takes energy into the system for the liquid to go to a gas phase. So when water evaporates, this is an endothermic. So the sign on delta H is positive. What's the sign on delta S? Now, we're going from liquid to a gas. So what's the entropy change of the system? Increasing, because we're going from a liquid to a gas, right? So this is a plus and this is a plus. All right? Did everybody get that? Good. Now, is it spontaneous? Is it spontaneous? Okay, Sabrina's shaking her head. Why? Why is it not spontaneous? Because it doesn't have the minus sign. Well, let's plug it in and see, right? Delta G has to be negative for this to be spontaneous, right? So let's plug this in. If delta H is positive and delta S is positive, so we have a positive number and we're subtracting T delta S, right? Delta S is still positive, so we're taking a positive number and we're subtracting something from it, right? So, is it spontaneous or is it not spontaneous? It depends. Depends on what?
Temperature?
You need a really high temperature. That's exactly right. It depends on the temperature. Because when temperature is high enough, then this negative value is greater than the positive value, and therefore delta G becomes negative. If the temperature is too low, then it's still a negative term, but now the absolute value of that negative term is less than the absolute value of the positive term, and delta G is positive. So in this case, it depends. It's only spontaneous at high temperatures. Now, how high, we'll see later on in the chapter how we can actually calculate what that temperature is above which it's spontaneous. So if the temperature is too low, it's non-spontaneous. If the temperature is high enough, it will be spontaneous. And as you learned from the video, any reaction that's spontaneous in the opposite direction, it's non-spontaneous, and vice versa. If we describe a reaction that's non-spontaneous as written, going from left to right, that means the reverse reaction is spontaneous. And by the way, I didn't mention it earlier, but I should emphasize, what are the units of T? This is in Kelvin. It's not degrees Celsius. And if you remember anything about Kelvin, there's absolute zero, all right? And you can't get any colder than absolute zero. So Kelvin, temperature in Kelvin, is always a positive number. That's why we use the Kelvin scale in thermodynamics, because that value is always positive, because it relates to the kinetic energy of the system. So it's always greater than zero. Okay, so in some cases, it's always spontaneous. In other cases, it depends on the temperature. let's see, when we separate a mixture into pure substances, and let's say in this case, I'm telling you, delta H is 0. So let's not even think, there's no heat exchange involved, let's pretend, when we're separating a mixture into pure substances. But what's the entropy? The entropy increase or decrease if we're taking a mixture, a homogeneous mixture, and we're separating it into its component parts? What do you think? Entropy is a sign of disorder. Here, let's go back to, I really like this example in the textbook of the gases, of getting the idea of how entropy alone can drive a reaction. Okay, we start with two gases separated by a divider. Gas A is on the left and gas B is on the right. But when we open up that divider, we know intuitively that the gases are going to mix equally on both sides, right? But what's the driving force for that? Where's the energy coming from to cause that random dispersion? Because we're not changing the pressure, all right? We're not changing the volume. The pressure is the same on both sides. There's no energy being added to the system. All we're doing is removing the door. Yet we know that these atoms are going to disperse in this way. And that's the driving force. We're increasing the entropy. The more disorder there is, the more randomly you can disperse the energy, you get increase in entropy. So this is your homogeneous mixture. Now I'm posing the problem. We take this and we get it back to A on one side and B on the other. We're separating the mixture. So the entropy actually decreases. We have more order. So here, delta S is negative. We have more order. All right, so this one's pretty straightforward. This is non-spontaneous. And we can see that if we plug this into our delta G equals delta H, which is now 0, so it goes away, minus T delta S. Well, if the change in entropy is negative, always, then delta G is always going to be a positive number. That's non-spontaneous. Okay? But as I said, any reaction that's non-spontaneous, the reverse then will be spontaneous. Okay? Why don't you guys, as a group, let's work through this next one. Nitrogen gas combines with hydrogen gas to form ammonia. Here's the delta H of that reaction. I'm telling you, it's negative 92 kilojoules per mole. So let's go ahead and figure it out. Is this going to be spontaneous or non-spontaneous?
There's the dispersion. So that would be increased.
Yeah, 4 on the left side, it's 2 on the right side.
The entropy increasing or decreasing, and why? Why is the importance? Because otherwise it's just a 50-50 chance. What did I tell you earlier about glucose? What's one thing you can look at in a reaction that will tell you about the entropy with respect to the phase of matter?
Gas.
Gas. Look at your moles of gas. How many moles of gas are in the reactants? 4 moles of gas. How many moles of gas are in the products? 2 moles. So if you just look at the moles of gas on each side, you can make a pretty strong prediction of whether the entropy is increasing or decreasing. Entropy is decreasing because we're going from 4 moles of gas down to 2 moles of gas. That's more organized. It's less dispersed. Okay? So that means delta S is negative here, which means here it's negative. So ultimately, again, we want to know, is this spontaneous? Is the overall reaction? We just established entropy is decreasing, so you might think, oh, there's no way that's going to be spontaneous. But remember, this is entropy of the system, not the universe. So we need to evaluate both delta H and delta S to tell if overall this reaction is spontaneous or not. That's what delta G is telling us. So what do you think? Is it spontaneous or not? Once again, if delta S is always negative, then T delta S, all right, is always a negative value, right? And we're subtracting a negative value, right? That makes it a positive. Do you all see that? Because T is always positive. So if entropy, if change in entropy is always negative, this value here is always positive. So whether delta G is negative or not depends on the temperature again, right? At low temperatures, if T is low enough, then this term is still, even though it's positive, its absolute value is less than the absolute value of enthalpy, so it will be negative. If temperature gets high enough, now this positive is greater than this negative, and delta G is positive, and it's no longer spontaneous. So this one is spontaneous at low temperatures. And you can see it from the math. If you can't see it from the math, just work with it a little bit tonight, and you'll see. It's a little confusing because it's minus T delta S. But just look at what that T delta S term always is. This is a great example, okay? You can look at this equation and you know that no matter how much of this reaction is going on, the entropy is always decreasing because you're going from 4 moles of gas down to 2. So delta S is always negative. I'm telling you that delta H is negative. That's a given value. You can look this up in Appendix 4 in the back of the chapter. So it's all dependent on the temperature. At high temperatures, no way. At low temperatures, yeah, it'll go. Here's an ice going to liquid water. It's the reverse of what we did before, right? Up above, we went from liquid to gas. Now we're going from, actually it's not the reverse, but it's similar. We're going from a solid to a liquid. And we're told that the delta H for that is positive 6.01 kilojoules per mole. Does that number look familiar to anybody? This is the delta H of fusion for H2O. Right? That's that many kilojoules of energy required for 1 mole of water to transition between the solid and the liquid phase. Right? If we have solid H2O going to liquid, we know that we need energy into the system, so it's positive 6.01 kilojoules per mole for 1 mole of solid ice to go into liquid water. If we're going the other way, if we're going from liquid into solid, it's the same 6.01 kilojoules per mole, but now we have a negative sign because the energy is coming out of the liquid. We're extracting the energy from the liquid. That gets it to go from the liquid into the solid. Now, if delta H, now in this case, we're writing the reaction this way, ice going to liquid. So delta H is positive. So let's write this. Delta G is equal to delta H minus T delta S. So delta H now is always positive. And delta S, we're going from solid to liquid. So is entropy increasing or decreasing? It's increasing. We're getting more random, right? Things can move around a little bit better. So entropy is always increasing. So we have the same situation that we had up above. It's only going to be spontaneous at high temperature. Once again, the T delta S term is always a positive value. So we have a positive and a positive, but we're subtracting, right? So at higher temperatures, this number now becomes greater than this number, so it's going to be negative. So it's only spontaneous at high temperatures. But we have practical experience with this. If you take, it's kind of shown on the next slide here. Here's the ice, and here's the water, okay? So energy goes in, let's put it this way, energy in, for the ice to melt into water. Does that happen? So, by the way, what temperature does this transition take place at? Under standard pressure, what temperature does this transition take place at? 0 degrees Celsius, right? Which is 273 Kelvin. So no matter what, when that transition takes place, the system is at 0 degrees Celsius. Even if it's like you take an ice cube and you put it at room temperature. Let's say you put it at 25 degrees, which is what this problem is posing. All right? At 25 degrees, we know that the ice cube is going to melt into water, right? We know this. So we know that it's going to be spontaneous, right? The ice melts spontaneously if we're at 25 degrees. What if we put the ice cube at minus 10 degrees? Is the ice cube going to melt? No, we know this, right? It's non-spontaneous at minus 10 degrees Celsius. When it's melting at 25 degrees, though, okay, the system is actually at 0 degrees when it's actually melting, okay? The energy is coming from the 25 degrees. It's going into the ice cube. But this actual transition happens at 0 degrees Celsius. I'm going to save the calculations on this page for the next lecture, though, because it's not enough time to get into it. So instead, let me spend the last few minutes just reinforcing some of these ideas, right? You can probably guess, looking at this, what is that magic temperature where this switches from spontaneous to non-spontaneous? What do you think it is? 0 C, right? If you're below 0 C, it's non-spontaneous. If you're above 0 C, 0 degrees Celsius, right? Now it melts spontaneously. Right? So just think about that when you think about what we have here in red. Now something else to keep in mind when you're going through all this stuff is the units. The units are unfortunately a little confusing here. All right, so let me be really slow and solid and emphasize that when we do this, okay, delta G is equal to delta H minus T delta S. The units of delta G and delta H are always in kilojoules per mole. But the units of delta S are in joules per mole. Why the convention is this way probably has something to do with what the values tend to be when we make these measurements. What it means for you, though, is that you have to remember or keep your eye on the units, because when you do a calculation like this, you're always given delta S in joules per mole and delta H is in kilojoules per mole. Delta G is in kilojoules per mole. So if you're calculating delta G, you got to make sure you make that adjustment. All the units need to be the same. It's a very, very common mistake that students make, is they don't convert from joules into kilojoules. Don't be that student, okay? So write it down really strong and nice big red letters.